Stanford Linear Accelerator in the US to bombard targets, revealing the quark structure of the proton. Back in Berlin, instead of kilometers, the Frank-Hertz experiment used an acceleration of only a few millimeters. Inside a glass tube like this, electrons are emitted by a hot filament close to a controlled metal grid that lets the electrons go through. On the other side, a second positive metal grid attracts and accelerates the electrons. The holes in the grid let the fast-moving electrons pass through. Given the potential difference V used to accelerate the electrons, we can calculate how fast they will be moving when reaching the accelerating grid using conservation of energy. The potential energy given by the charge of the electron times the voltage will become kinetic energy 1/2 mv squared, from where we can solve for the speed and find this relation. Frank and Hertz use a variable voltage to analyze the behavior of these electrons over a range roughly between 1 and 15 volts. Plug in the minimum value, we get that the electrons will move very fast. The next step was to introduce a target for these electrons to collide with. The tube contains a drop of liquid mercury. Placing this tube in an oven at 150 degrees Celsius, mercury will evaporate from the liquid drop, filling the tube and the path of the electrons with a vapor of mercury atoms. These atoms are of course moving due to their thermal energy. We can use conservation of energy to estimate how fast they move. The thermal energy can be written as 3/2 kT, where K is Boltzmann's constant and T is the temperature in Kelvin. Setting this equal to their kinetic energy, we found that the average thermal speed of the mercury atoms is given by this expression, where uppercase M is the mass of a single mercury atom. To find the mass of a mercury atom, we use that its molar mass is 200.59 grams per mole. Dividing by Avogadro's number, we get the mass in grams. Converting this mass to kilograms and using the temperature in Kelvin, we find that the average thermal speed of the mercury atoms is slightly over 200 meters per second. Here we notice that the electrons in the Frank-Hertz tube move thousands of times faster. Therefore, from the point of view of these electrons, the mercury atoms are practically at rest. Let's now consider the collision between one of these fast electrons and a mercury atom. Conservation of energy and momentum can be used to determine the speed of each particle after the collision. Solving for the atom's momentum uppercase P prime in terms of the electron's momentum P and taking its square, we find this relation, where theta is the angle between the electron's momentum before and after the collision. We can find the term on the left-hand side from the energy conservation relation. Plugging it here, we get a quadratic equation. After some algebra, we find that the speed of the electron after the collision is this. We can simplify this expression by noticing that the mercury atom is almost 500,000 times more massive than the electron, so the ratio of their masses can be neglected. And this expression reduces to simply V prime equals V, where I have ignored the unphysical negative solution. This result means that the electron bounces in some direction but without changing its speed. This type of collision is called elastic scattering. From the energy condition, we can directly see that the mercury atom remains at rest, which makes sense because the atom is too massive. This collision can be visualized as a ping pong ball striking a bowling ball. The ping pong ball will bounce with the same speed, and the heavy bowling ball will not move at all. These are the calculations that Frank and Hertz did in late 1913. Bohr's atomic model was less than half a year old and not widely known. Spectral lines were still a mystery for many. Frank and Hertz imagined that if they could excite an atom by hitting it with high-speed electrons, maybe the atom could borrow energy from the electrons and then give off the excess energy in the form of spectral lines. The boring expectation, according to the calculation that we just did, was that electrons will simply elastically scatter off the mercury atoms. But Frank and Hertz hoped to excite the atom so that at some point the electron could undergo an inelastic collision instead, transferring some of its energy to the atom. These inelastic collisions would make the electrons reach the accelerating grid with less energy than expected. Here Frank and Hertz included a way to distinguish these low-energy electrons from the normally expected high-energy electrons. Just like those popular signs in amusement parks that say, "You must be this tall to ride," Frank and Hertz added an electrostatic way to reject low-energy electrons. In 1902, Philip Leonard introduced the so-called stopping potential to slow electrons down in the photoelectric effect. The same idea was later used by Robert Millikan to determine the kinetic energy of photoelectrons, which led him to confirm Einstein's predictions and win the Nobel Prize. Frank and Hertz included a stopping potential behind the accelerating grid. In this way, the experiment rejects low-energy electrons. Notice that if the collisions between electrons and mercury atoms are elastic, there will be no energy loss. The electrons will bounce around, but they will arrive at the accelerating grid as if the mercury atoms were not there. Frank and Hertz intended to check if any deviation from these perfect elastic collisions of electrons occur, and from these infer features of Mercury's atomic structure. This is how the experiment works. The accelerating potential can be varied between 1 and 15 volts. On their way to the positive accelerating grid, the electrons will collide with the mercury atoms and elastically scatter. Then they will go through the accelerating grid, after which they encounter a repulsive electric field. As long as the electrons have more energy than the stop-it potential, they will continue to the collector electrode. The collector's current is a direct measure of how many electrons reach the collector. Therefore, as the accelerating potential is increased, the current through the collector will also increase. There is a fantastic film by the Physical Science Study Committee published in 1961